You may start.
Okay. So thank you, Professor Dhaka, first of all, for this invitation and for giving me this opportunity to present my work. So hello, everyone. So myself, Pradipta, and I am a particle physicist. So my main area is exploring the origin of the elementary particle interaction. So within and beyond the standard model. But today we will learn about some things which is really interesting, and that is about the neutrino physics. And in order to know that, let me emphasize on certain peculiar aspects of the neutrinos. One thing, please feel free to interrupt if things are not clear to you at any point of time. So it is known. So so that is the reason why today I will talk about the Bogart of particle physics. Now, those of you who are Harry Potter fan, you know that Bogart is nothing but it's a kind of ephemeral object which can change its shape, and that is precisely the main aspects or the main motivation of giving this talk, as you will see subsequently. So, since I mentioned about the Bogart of particle physics, so first of all, then immediately I need to define the Hogwarts of particle physics. Now, what is the Hogwarts of the particle physics? It turns out the Hogwarts of the particle physics is known as the standard model of particle physics. Now, what is the standard model of particle physics? So basically, if you remember, in a school, like there are certain students, teachers, and there are a set of rules which you need to follow. So in the same spirit, the regime of the standard model, it has certain inmates. So that is known as the elementary particles and mediators. So these are something like the students or this poor student, as you can see in this picture, of the standard model. Now there are also certain rules and certain laws. In other words, there are certain interaction which actually describes how elementary particles works. And it turns out that out of 4 fundamental interaction, as you can see on the slide, so we know there are 4 fundamental interaction in nature. The gravitational interaction, which is responsible for the motion of the Earth around the sun, or the galaxy formation and things like that. And then you have the electromagnetic interaction. You know that a positive charge and the negative charge, they attract each other, and the similar charges, they repel each other. So this is known as the electromagnetic interaction. And then you have something, I hope all of you are familiar with the beta decay. Is it or is it not?
Yes, sir.
So basically, if you know about the beta decay, then you know that is something that is, the basic mechanism behind the beta decay is another new force of the nature. It's a fundamental force that is known as the radioactive force or the weak force. And finally, you know that the nucleus, it's a small object, and all of you know that inside the nucleus we have several, if you consider hydrogen, it's a simple one. But if you go to more complicated stuff, even helium, there are like 2 protons and 2 neutrons. Now it's very legitimate to ask that how on earth inside this tiny space 2 protons are staying together, because we know both of them are positively charged, and they are staying together because it turns out that the repulsion, or I would say the repulsion that is mediated or produced through the electromagnetic interaction is way weaker than another fundamental force of the nature, which is known as the strong force, which is represented by this. And if you actually do a relative strength, if you try to arrange this force in terms of their relative strength, then definitely strong interaction, as you can understand by its name, it is you can consider it to be the order 1. Then you have the electromagnetic interaction, and I'm sure that all of you are familiar with the fine structure constant. So roughly the strength of the electromagnetic interaction is represented by the fine structure constant, which is given by 1 by 137. So it is roughly 10 to the power minus 3. Then you have your weak decays, and finally you can calculate and show that the gravity is actually the weakest and the rough strength compared to the strong force. If I assume that the strength of the standard force, a strong force is given as 1, it is given by 10 to the power minus 39. But unfortunately, although we are claiming that the Hogwarts of the particle physics is the standard model of particle physics, but unfortunately, gravity, that is the fourth fundamental interaction of the nature, is not included in the theoretical formulation of the standard model. So even moving further, immediately you can see that there exists strong motivation or strong urge to consider physics beyond the standard model because gravity is not included. So it is natural to look for some model where all these four fundamental interactions are included. So with this, I will move to my next slides. So let us take a look at the inmates of the Hogwarts of the particle physics. So they are nothing but the elementary particles. Now all of these are elementary particles, and you can see that in this picture I have also written down their masses, their electrical charges, and their spin. Now spin is something which is not like a spinning top. This spin is a quantum mechanical spin which has no classical analog. I mean, you can actually try to spin a top and you can say like this is spinning, or you can think about the spinning motion of Earth about its own orbit, but this spin is something very different. It is something similar, but it is hard to realize in terms of the space-time understanding of the physics. Now it turns out that out of these elementary particles, there are actually 12 elementary particles. So they are known as the quarks, which is given by this purple block, and they arrange in different families. I'm not going to the details. If you're interested, we can discuss. And the green ones are the leptons. Now, if you take a look in these elementary particles, there is one thing which is really interesting. You can see that the neutrinos, there are three flavors of neutrinos: electron neutrino, muon neutrino, and the tau neutrino. They are spin-half particles, so they are fermion, but their masses are 0 in the original standard model. Now in the red, you have the mediators. So what is the role? I mean, what are the role plays by the mediator? So mediators are basically like the postman. So they are actually, so a force is something that actually binds together or via which one elementary particle talks to another elementary particle. Now, this information of carrying this message is the responsibility of this mediator. So when it is about the strong interaction which holds the nucleus together in spite of having too many positively charged protons, it is the gluons. There are 8 of them. Then for the electromagnetic interaction, we have photon, which is again a massless. And finally, for the radioactive decay or for the weak force, the interaction is mediated by Z boson and W boson. Now this W boson is electrically charged, so there is W plus and W minus. And finally, this noble guy, which is the Higgs boson, which is probably the most infamous particle in the history of the particle physics, because for about 60, more than 60 years, I mean, the theory of the need of the Higgs boson was postulated in 1964, and it was eventually discovered at the Large Hadron Collider, also known as the LHC, on the 4th of July 2012. Actually, it was discovered a few months earlier, but this is the date when both the experimental collaboration, the CMS and the ABLUS, made public announcement. And just to give you an idea that when we talk about these elementary particles, you can immediately understand that we are no longer in the macro world, but what is the meaning of elementary? That means we are in the micro world. For example, if you want to consider a particular unit system, which is very interesting for the particle physics, which is known as the natural unit system, their C is 1, as well as the Planck constant is 1. To be precise, it is the reduced Planck constant. And you can see in this unit, if you consider C is equal to 1, one electron volt is equivalent to 10 to the power minus 36 kilogram of mass, which is extremely, extremely tiny. Okay. So, any question till now? Any doubts? Any comments?
Sir, how Higgs boson was discovered?
Sorry. Yeah, there was a question, please.
How Higgs boson was discovered?
Okay, so how Higgs boson was discovered? So it was actually discovered by something. So basically, there is certain kind of diagram where two of these gluons are fused together by some interaction. I'm not going into detail, and there is a coupling of this gluon with this Higgs. And when you have this Higgs production, of course, we cannot decay any particle unless we cannot detect any particle unless it is decaying. So after the production, the Higgs can decay into different other elementary particles. One of the possibilities is that the Higgs is decaying into a pair of photons. Now, in fact, that was one of the most prominent channel which we have used, or the experimentalists have used to detect the Higgs boson. So there are certain experimental technique like mass reconstruction. They actually captured both these photons which were coming out of the Higgs boson using some experimental techniques which are rather complicated to understand, at least at your level. And then they try to do something which is called the mass reconstruction. So when they did this mass reconstruction, they realized that this mass is actually peaking in the vicinity of 125 GeV. And that is the reason why they eventually concluded that the mass of this elementary particle lies in the vicinity of 125 GeV. Is it fine, or you have more doubts?
Sir, it's fine.
So, how do we get protons or neutrons from this table?
Sorry, how do you get protons?
Protons or neutrons? There is no mention of either in this table.
Exactly, that's a very good question. So as I said, that if you consider, say, the scale of nuclear physics, what you mentioned, that is it's a very nice question. So if you consider the scale of nuclear physics, at the level of nuclear physics, which is typically a length scale of 10 to the power minus 15 meter, you know that is the typical diameter of the nucleus, or femtometer. At that length scale, the typical energy is MeV, and that is basically at most 1 GeV. That is typically the rough mass of the proton and the neutron. But if you consider a probe which is way powerful than the nuclear, say the Rutherford alpha scattering experiment, suppose the LHC. So at the LHC, you are actually colliding proton with proton at 14 TeV. So 7 TeV proton head-on collision with 7 TeV proton. So there you have the chance to probe a length scale which is as small as 10 to the power minus 20 meter, which is 5 times smaller than the typical diameter of a nucleus. So if you consider a probe which is as deep as this, there you will see that protons and neutrons, which was appearing as elementary particle, they are indeed not elementary particle. In fact, there is a specific mechanism which is known as the deep inelastic scattering, or typically abbreviated as DIS, which were used to probe the substructure of proton. And then they realized that proton is in fact a composite object, and the quarks, so quarks are much more elementary or fundamental, and the quark structure of a proton is given as UUD. So a proton is a combination of one U quark with spin down and another D quark. And if you actually now consider their electrical charges, you see that the electrical charge of up quark is 2/3, whereas the electric, sorry.
Yeah, it will be total to 1, up, down.
Exactly. And in the same way, if you consider UDD, you will get a neutral object, and that is nothing but the neutron. Of course, there are certain things, since you mentioned this, you must realize that if you roughly take a look at the masses of this quark, you can see the collective amount of UUD is of the order of 10 MeV. On the contrary, you know that for a proton, the mass, what is the mass of the proton? It is of the order of what?
It's a 900 or something.
Exactly. So that is way larger than their quark composition. So there are certain mechanisms for that, and that is something related to this I would say certain features of the strong interaction, which when you are going to learn about the quantum field theory, then you will understand it in a, I would say, in a much more elucidated or much more in a proper way. Okay. So good to go, or you have any doubt still in this slide? Okay, because the thing is that in the standard model, most of the, I mean, you see, when you consider the standard model, so first of all, what is a model? A model is guided by certain mathematical principle. Now it turns out that if you follow that mathematical principle properly, then all the particles of the standard models are forced to be massless. But in reality, when we detect, I mean, you know, like how electron was discovered by J.J. Thomson long back. But when we have detected those elementary particles, we realize that they are massive. So there was a question that my theoretical framework is suggesting that everything should be massless to have a self-consistent theory. On the contrary, my nature or my experiment is giving me that no, see, at the end of the day, what you are detecting, they are massive. So there was an apparent glitch between these things, and it turns out the way scientists have proved it, that both these observations were true. Now, that is the reason people have invented this Higgs mechanism, which was invented by Peter Higgs and also few other notable scientists, who realized that there are certain methods by which this Higgs boson actually enters this play, and it helps this elementary particle to get their masses. And that is one of the reasons, because of Higgs, everything is massive. That is the reason why it is popularly known as the God particle. Is it fine? Okay.